All right, we need to revisit the scope of work. So we'll talk a little bit about safety, the manufacturing processes, joining, fastening hardware, physical, environmental. When we think about safety, we talked a little bit about pinch points, the rotating mass, RPM and torque, vibration. Is that gonna affect the sound level? Actuation, linear movement, force and frequency. Mass, is it really small, really large? Does it have the potential to tip? Are we dealing with elevated temperatures, super low temperatures? To that end, is pressure, is vacuum an issue? Shear and sharpness is uh, where the material as it's moving, does it have a cutting action? So I'd mentioned the sound level. We're going to have to we're hearing protection around, and then is this going to have a safe work zone where we need guarding, emergency stop, power isolation? We get to environmental things like the wet areas. So in our manufacturing processes, some of the common uh, items that we'll go through have access to, whether they're in-house. It's going to be important to know what you have access to, if you have access to any of these within your organization, or if everything's sent out to a vendor to provide these services. So the considerations are the material. Harder materials require specialty tooling. That's why a lot of this, if we can get away with aluminum or plastic, is going to be a more desirable, cost-effective to our process. So, and then what levels of precision and accuracy? What kind of surface finishes do we need? In the joining, we have the screws, bolts, and nuts, washers, the pins. We just talked a little bit about the bearings and bushings, clips and rivets to retain, O-rings, seals, gaskets, aluminum type extrusions, and then welding. So all of our mechanical fitments. The threads. I think we saw this when we did the thread, but this is a quick review. The machine threads run like quadruple lot, but I don't like to think about those. They're really small. The machine threads 0 through number 12. This will give you the calculation for the major diameter, the pitch, and the minor diameter. So the important one here is the first number in our series, 1032, 440, 632. Knowing which ones are most commonly used. But the important formula is the number in front times 13 plus 60 will quickly give you the major diameter. The fractional is the first part, and that could either be read as 0.250-20 or quarter 20 in our naming, and then we again have the pitch and calculate the minor diameter. The metric, I've done it quite a bit, and I always manage to get myself in trouble doing the math in my head, but the 39.37 inches in a meter divide by 1,000, 0.03937 is 1 millimeter. That is really close to 40 thousandths of an inch. Makes the math easy. As I mentioned before, if we were to take this M6 times 4, the 0.04, that would give me 240 thousandths. And the actual is about 236. So very close, very quick translation. And then metric being the oh so complicated, dripping with sarcasm, we take the first number and subtract the second number, and that gives us our major and our minor diameters. So an M6 by 1, major diameter is 6, 6 minus 1 is 5. Right, so you can have access to all that information to be able to check your designs as you're going through it. On our physical considerations, The static and dynamic forces that we're dealing with, pressures, torque, vibration, acceleration, thermal, electrical, and fluid. And this is where we get into that simulation or finite element analysis, being able to do basic prove or disprove that, really, I mentioned gross errors. We're looking for gross errors. There's always going to be unintended, unanticipated consequences of any mechanical system. It's how much you have looked into your magic crystal ball of design intent and said, at the end of the day, this is going to be an acceptable level, and we can make those changes and updates as we go. In the environmental systems, we're concerned about corrosion, outgassing, lubrication. We talked a little bit about the bushings, permanent lubrication in the roller bearings or in the bushings. Thermal cycles, hot and cold. Is this going to be exposed? Is it going to be in a temperature stable environment? Is it going to produce thermal hot and cold in its operation? Are there any toxicities um, in the process or in the materials that we're using, and reactivity to other chemicals or gases that are in the area? So there are certainly things that we would not want to use aluminum, that we go to stainless steel because of the types of interactions that we can reasonably anticipate. So all this comes down to product life cycle management. And the other side of the life cycle management is once the assembly, the product has gone through to its end of life, how do we recycle it, repurpose it, basically go so that it is not just sent to the landfill. And then our measuring standards, we've talked a little bit about ISO and ANSI are the organizations, and they refer to, ANSI refers to ASME, SME, and SAE, automotive, manufacturing, and mechanical. For those, the recommendations for those, and they are the authorizing organization that gathers up all that information and says, as a group, this is what we're going to do. And then, of course, our standard units of metric and inch, and we're looking for industry alignment and consistency in our process. When we get to measuring and inspection, we're putting all of these tolerances on. If it can be measured with a scale, a tape measure, ruler, then you have pretty open tolerances. So calipers go a little bit further, and micrometers even go a little bit further. And when we get down to the coordinate measuring machines, that is a semi-automated process that's going to be able to inspect our parts. Protractors and sign bars for angles, gauge pens for holes. When we get to those really fine 10 millimeter holes, I'm going to go to my gauge pens and measure the set of pins in thousandth of an inch increments and be able to reasonably verify the diameters that were drilled, reamed, or otherwise in their manufacturing process. Optical comparator uses slides and overlays, shines light through it, and can be a very quick, easy way to verify angles and geometries. And there's a certain amount of magnification that comes with that. So you can look at the detail of the part. And then vision systems improving more of a computer type system. And then we get into the documentation, which is what we've been working on. And we haven't really looked at the DIM expert or tolerance analysis, but we will get into that with also with the model-based definition. With our drawing modules and the output, then we're really looking at what are the working documents, the hard copy, paperless. Are we looking at it in a viewer, PDF, e-drawings, some other program to be able to view without having to have a copy of SolidWorks on every machine. And so scopes of work, scope of work, and then the quotes and estimate, and our working drawings become our documents. So all of this ties in, and we're looking pretty much at the scope of work. We really want to start and end with the scope of work, because that's going to drive a lot of these decisions. The quote and the estimate are going to be based on this contractual agreement that is generated by the scope of work, and the working drawings are the end result that says this is what we're going to manufacture, this is what we've charged you for, and this is our end product.